This lecture of today is the second part of the analysis of emerging behavior. Yesterday, lecture 9 was already like that, but this one, which is lecture 10, is going into some more depth in a more general approach. And then we relate it now to the notion of strongly connected components. And that makes it possible to address any connectivity type of a network because you just consider the strongly connected components. That's what we do today. It relates to the advanced part of the assignment of today. So this is the same picture as yesterday. What we do is we try to find properties of the network structure that from which we can tell something about the behavior. So the ideal that you can, from the properties of the network structure, you can derive completely what the behavior is. That's asked too much. That's not possible in general. Although this determines the behavior anyway, it's a deterministic system, so it should be determining the behavior, but how to know all these properties and how they determine it is only to a certain extent possible. So that's what we do now. We try to find at least some of these implications in these ways how the structure influences the behavior. So this time we will look at some network like this. In a previous lecture we considered networks that were almost strongly connected with only a few independent states connected to it. But that's still, the network as a whole is still almost strongly connected. But now we don't have that limiting condition. Now we have just a general network. And you can see here that there are, this is not a strongly connected network because you can go here, but you can never go back, for example. And also here you can go there, you can never go back. So this is also the example I briefly showed on Friday, actually, I think. So this is these are the role matrices describing the network. It's just very simple. All are Euclidean functions of order 1, which is just a scaled sum. And this is the normalization by scaling factors here. But the rest is just simple. But there are arbitrary connection weights. Notice that in the theorems that we've considered this time, like yesterday, there are no limitations on the values of the connection weights. So that's an important issue to consider. So we leave that aside and still can draw some conclusions. So this example shows this behavior if you run it. And that's a bit more complicated than previous examples because now we see some clustering here of the state values, 4 of them. Also here, if you look well, you see clustering 3 of them. And then these are just different. So that picture is more, in a sense, you can say heterogeneous. It's different phenomena visible here. And we want to explain, to analyze these phenomena one by one, all of them. So there is a stationary point for here. So if you want to analyze the stationary points, you can see a small top here, maximum, and a small dip here. These are stationary points. So for considering stationary points, you can find some things. There's also one here, here a top and a dip. But there are, of course, there are also stationary points at the end, and that's just all are stationary then, and that means that there is an equilibrium state. So most of the things of today will focus on that part. So these are the definitions of stationary point as like yesterday. This is the criterion that is used to check whether something is a stationary point. That means that the aggregated impact defined just by this, you have the single impacts of the incoming states for the state Y. And you apply the combination function on it. In our case, for today and also in the assignment, we will just consider the scaled sum. So then you would take the sum of these and then dividing it by the scaling factor. So that's the equation for the stationary point. That's the criterion that you can just derive immediately from the structure of the network. And then we have this notion of the different definitions of some notions that are used for the combination functions, Scalar-Free and Monotonic. Monotonic increasing, strictly is also the same as yesterday. So in the things that we find today, exactly the same properties of combination functions like yesterday will be assumed. So that's not new, it's just the same. So all Euclidean combination functions do satisfy such properties, and especially the scaled sum, but not the logistic functions, but also the geometric mean functions as well. So let's now look at the network structure in comparison to the different phenomena here. And the different phenomena, I mean, there are one constant and three coming together here. There is one cluster coming together here, and there are different single values. So these are different phenomena. And how can that be related to the network structure? Because it should have some relation to the network structure, and that we want to find out how that is. So this is the x1 to x4 here coming together. This is the x5 to x7 coming together. And these are 8, 9, and 10 that just are different. So how does that relate to this network picture here, the connectivity? Well, let's first look at these, the 5, 6, 7, and they come together here, and they relate to that. So that they here form some kind of cycle here, apparently has influence that they come together here. That's one relation that we consider now, that we can hypothesize that such a relation should be there. And then the other ones, they are these four, but this is not just a cycle, this is also this structure. This has a more complex structure already because there are different things here. And then the limit values of the other ones, these ones, they are different, but they're still between these two. There's also something to observe. They are not going outside these borders. That's also something, a phenomenon that we want to explain. So then we come back to the definition of strongly connected components. That's just the same as we already had earlier. And on Friday, especially, I have explained the notion of strongly connected components. So they can be determined by picking a state and then adding all states on cycles through that state. So I showed it like this. So you can have all cycles here, all cycles from another point here, and all cycles from another point here, and all cycles from another point. So these are the connected components then of this network, but they also have still some connections. But these connections can never be a cycle again because you already locked up the cycle. So there is no error here that makes a cycle of the whole, because then you would have one strongly connected component. The whole network would be strongly connected. So this is interesting to see that you cannot come back. There cannot be cycles, and I will come back to that soon as a more general idea. So in this example, we have these ones. I think that we also did that on Friday already. So these are the strongly connected components, and they should have some relation to the phenomena of the behavior that we want to explain. So that's we want to do it now in a bit more detail, how this relation exactly is. And you see that these were together in one phenomenon in the example, but now they are in different strongly connected components. So that's already a bit different than maybe you might expect beforehand. So what we do is we take a more abstract view on the total network called the condensation graph. Then we consider the components as the nodes, and the connections, they are just when there are states within the components that are connected. So in this case, these are the components. Then these become the nodes of a condensation graph. So this is the condensation graph, but the nodes are a bit big now. So, and these are the connections between these nodes. And finally, we have just this graph. So a very complex network with maybe 8 strongly connected components, but maybe hundreds of nodes, can be reduced then to just the number of connected components, strongly connected components. And you see here that this is not cyclic graph. What I already suggested earlier, that you cannot have cycles at this level anymore, because otherwise it would become one strongly connected component. So that means this is an acyclic graph, and these are a bit easier to handle than general cyclic graphs. So, and that's what we exploit here now. So no cycle, all cycles are locked up in the components. Then there is this theorem in the literature. There is literature about this going back to the 1960s. So it's already a bit longer ago where such theorems can be found. So and always this condensation graph is acyclic. That's just a theorem in that literature. And that means that this is indeed acyclic, that we already see. But then a next step in an acyclic graph, and that's in a different part of the literature on graph theory, you can do some stratification. You can say, well, these are the starting points. We call that level 0. Then there are points that can only be reached in one step from that we call that level 1. And then there are components that can be reached not only by one, but also by more steps, and that we call that level 2. So this shows a form of dependency, because they are not dependent, like C1 is not dependent on any of the others. And C2 also is not dependent on any of the others. So that means you can study them separately. And this one is only dependent on that, not on these two. And C4 is only dependent on these two, and directly dependent and indirectly to that. So that's the most dependent component, you can say. So we will exploit this dependency overview as the basis for the types of relations we will find. So this first part of the main theorem about this considers the level 0 components. But remember, the level 0 components are not influenced by any other components, so they are just on their own. Therefore, they look a little bit like what we talked about yesterday, the strongly connected networks. So then the aggregation conditions are the same as yesterday. About the combination functions, like the scaled sum satisfies these conditions. And now we have all states have the same equilibrium value, like we had yesterday. So this is not really different from yesterday in each of these components. And we also have a relation to the initial values. If there are initial values that have certain range for these level 0 components, then this final common value will also have the same range, or stays within that range. So we will come back to that, indeed that happens in the example. So that's for the level 0 components. And in this case, a special case, if all initial values are the same, then you will also have a common value in general. So this is an explanation already of part of the pattern that we saw, the patterns, the phenomena. And we found now that the level 0 components, they are the C1 and the C2, so these two. And that relates to this one. So this one, that means that the x1 has a common value, but only x1, so that's just its own value. That's not so surprising, because now it goes only about x1. We didn't consider this one yet. But this one here is a bit different. Now, indeed, this explains this theorem that they come together. And actually, this could be explained as well by the things that we had in the previous lecture yesterday, because then you can just consider this as a separate network that is not influenced by anything of the rest of the network. So that's one step. So we have already explained this part, and that this is constant, although this is not so surprising, of course. So then we go for the other components. They are not level 0 components. So we have now had level 0 components. Now we step to the other components at the other levels. So therefore the main theorem goes further. It has the same aggregation conditions like we had always. And then if you look at a level not 0 component, then there are previous levels which have connections to it. Because if there are no incoming connections for a component, then it is a level 0 component. So therefore, if it's not a level 0 component, there should be some connections from previous levels, from earlier levels. And then let's say that these ones, and then there is a relation between the values in an equilibrium of these and the value in the component C. And it's like this. Again, if there are equilibrium values in these preceding components, in the dependency graph, in the condensation graph, and they have values in some range, in a range between V1 and V2, then also the equilibrium values in the C have the same range. They are also within that range. So that gives some relation already that this range cannot be increasing. This range can only become smaller of these values. And well, if they have the same value, then you will also have the same value in your C. So let's see what we can find here. So we can consider first this C3 at level 1. It has only one incoming connection. That's the one from C1. And that was the one that already had this constant value there. And so it's this one that we are considering. So therefore, there is only one value incoming. So therefore, it should get the same value. So now we have an explanation why these values all become the same value. And in principle, why they become the value of x1. So they all join x1. That's now explained by this part of the theorem. So that's this part, and then we finally can go to the next part. The last component, C4, that has incoming connections from here and from here. Now from the C3, that has the value 0.9, and the C2 has the value 0.3. So you have a range here of values that comes in different values. And indeed, now you see that the values of these states in component C4 are between these values. And that's also what the theorem says. So by these theorems now we have explained all phenomena here. That means if you do such a simulation and you find that, for example, this one goes below that, or this one goes up above that, then you know something is wrong. So then the idea of verification comes in again. You can verify your model by checking whether your simulations, some example simulations, indeed fit in these theorems that we had. And if they don't fit, you will feel disappointment because you will think your model is not quite okay. That's true, because it should be corresponding to these results in the theorems. But you should also be happy on the other end, because you can improve your model. Otherwise, maybe there is an error in your model and you would never discover it. So therefore, be happy that you have such verification options, even if you are disappointed if you fail for it. So that's the main message. Let me make some further steps, but this is already the main message that comes out of this, lecture of today. I have some condensed theorems that relate also things to the at once. This is a theorem that is a kind of transitive closure of the other theorems, you can say, that relates immediately at level 0 to all other states, just by eliminating the intermediate steps. So then you have once immediately how all states in the network relate to the level 0 states. So then that's also here. Then we have the relation to the initial values. Here you can see that the initial values have these types of effect And then you can also apply this and to check your model. I think this is all that I wanted to discuss for now. So we have this graph theory tools based on strongly connected components that we now have exploited. And we have the same aggregation conditions again, like in the other case. And together we have now a main theorem on how for any connectivity, so we don't have any limitation anymore in the connectivity of a network. It can be applied to all types of connectivity. We have now some results to analyze them. So not only for the strongly connected networks, and also not only for the linear functions here, although in our examples, we will use it now for scaled sum, which is a linear function. Okay, is there any question about this thing?